Okay, I'm going to be speaking about the Orion vehicle and the capability that it's going to provide us in cislunar space. And I'm going to walk you through the initial exploration mission 1 and 2 missions, which test the capability before we actually move on into some bona fide real missions. Okay, so the first thing I want to point out, because some people don't know or have already forgotten, is that the Orion vehicle has flown already. In December 2014, we had Exploration Flight Test 1, which took the vehicle into an extended orbit on a Delta IV Heavy, and this allowed for a relatively high velocity return to test the heat load capacity on the vehicle to make sure that it survived and then eventually that crew would survive upon re-entry. The next steps in the development of this program will launch the Orion vehicle on the SLS, or the Space Launch System. The first of those two missions is called Exploration Mission 1, EM1. This will be an uncrewed beyond Earth flight. That's what that BEO means. It was originally scheduled for 2017. That slipped to 2018. The idea here is to, again, test a high velocity return. It'll re-enter the Earth's atmosphere at about 11 kilometers per second, just underneath the escape velocity. This will be a 7-day mission, so we'll also add duration onto this capability. It will orbit the moon on a free return path. So it's a relatively simple mission. The details of that mission are still being worked out, and I'll say a little bit more about that in a moment. The second of the two missions, Exploration Mission 2, will be crewed. It's scheduled for 2021. That also may slip. This is going to be a longer duration mission, 10 to 14 days. And this, you see it in a free return orbit around the moon, but in fact this will probably be either a distant retrograde orbit or a halo orbit about the Earth-Moon L2 position. Now, as we look ahead to the missions, there's been some discussion about the potential payloads on them. Obviously, the crew are going to be busy just checking out the vehicle on EM2, but they are going to have some time to do some science. One of the activities associated with these launches is the deployment of CubeSats. Other people have talked about that, and we'll talk about that more, so I'm going to not address that topic, but there is the capacity to carry other instruments. One potential instrument might be a high-definition camera to image the moon when it passes 100 kilometers over the lunar surface, as you see depicted here. This, I think, is very important, both when we achieve orbital status and eventually when we get it back on the surface. I think too many people in the public have a grainy Apollo view of the lunar surface. I think we need to give them a polished, modern, high-definition view of the surface, and I think that they will be amazed at the lunar surface once they see that type of imagery. An additional instrument might be another camera designed to detect impact flashes on the far side and or in the nighttime hemisphere to complement ground-based measurements of the near side. In the upper inset diagram is a map of impact flashes that have been detected by ground-based assets that are run by the Marshall Space Flight Center. In fact, this graphic comes from Bill Cook and Daniel Mosier at Marshall. And the idea would be when the Orion vehicle is on the far side of the moon to make a similar set of measurements. On average, an impact flash down to magnitude 9 occurs every 2 hours of observing time, which would be about 12 per day, so dozens could be seen during a single mission. I think it's also important to consider the deployment of radiation detectors for measurements external to and internal to the Orion crew capsule to test crew exposure models. If Orion is being designed for long duration missions, and so it is going to be important to determine exactly how much shielding one has inside that vehicle, or in the ESA-provided service module. Potentially two instruments that together measure the ionizing radiation and high-energy neutron flux could be considered, such as a tissue-equivalent proportional counter, usually described as a TEPC, and a borated plastic neutron detector. Now, something that I think you're going to hear more about later today is the possibility of using the lunar far side as a radio-quiet astrophysical or astronomical observatory. That concept is based on observations made way back in 1973 by the RAE-2 spacecraft, when it was an 1,100-kilometer circular orbit about the moon. If you see in this graph, which I see is too bright, we have lots of noise, and then you see an occultation on the far side, and the radio noise plummets. This is what the astronomical and astrophysical communities would like to take advantage of. It occurs to me that the Orion EM missions would be a good opportunity to actually make more modern measurements on the far side to compare them with the 1973 values. Finally, and perhaps most importantly, would be the consideration of deploying a communication asset on the far side. This is not a new idea. This again goes way back to the early 1970s. You could consider two types of options: a low data rate test article, or alternatively, and it would be my preference, to deploy a stable asset for many years that provides greater than 1 million bits per second data rate from the surface to the moon. That's the type of data rate that you're going to need, for example, if you do HD TV from the lunar surface. Okay, so that's the EM1 and EM2 mission. Beyond that, ISEG has been developing a roadmap, and the next step in that roadmap is human-assisted sample return, and now I'm going to walk you through some of the options for that type of mission. First question you have to ask is, where should human-assisted sample return go? And there's a couple of ways of trying to make that assessment. One of the ways is simply to compare where we've explored in the past. Okay, we've had over 24 missions to the surface of the near side, and zero, nada, none to the far side. And so I would advocate we should explore the unexplored and go to the far side. Okay, that's a rather subjective assessment. I'm not known for subjective assessments, and so let's look at this a little bit more objectively. We have this NRC 2007 report called The Scientific Context for the Exploration of the Moon. Through the predecessor to SURVEY, the NASA Lunar Science Institute, we conducted a 6-year series of summer studies to evaluate where these science objectives could be addressed on the lunar surface. And one of the outcomes of that study is that the Schrödinger Basin, which is within the South Pole Aitken Basin, is the highest priority landing site. Okay, again, it takes us to the far side. If we flew a mission, it would have this form. We'd have the Orion vehicle in a halo orbit, potentially around a distant retrograde orbit, but studies have shown that the halo orbit around the Earth-Moon L2 position is favorable. The crew would teleoperate a rover on the far side surface in the Schrödinger Basin, which would collect samples and then launch them to rendezvous with crew in the Orion vehicle. Geologic measurements would be made in situ. That sample would be collected, and as I said, collected by the astronauts in orbit and then returned to Earth. So there's a lot of science importance to that mission, but it also has some benefits for the exploration program. It will again demonstrate the Orion's capability for high-speed Earth reentry. This will provide an opportunity for a long-duration mission, up to 35 days long in translunar space. Crew will travel 50% farther than Apollo and spend 3 times longer in deep space, and allow them to practice teleoperation of rovers, which is a Mars-forward technology. And this concept is described in a paper by Burns et al. In the Advances of Space Research. Okay, we've done some detailed studies of this concept with the Lockheed Orion team. Here's a graphic from Josh Hopkins, who's been working with us. This is a COM map showing that we have complete COM coverage within the Schrödinger Basin for periods of 16 days, basically the entire daylit or sunlit portion of time that the robotic asset would be on the lunar surface. So from a COM point of view, this mission works. This is the type of orbit that one would follow. You would launch your robotic asset first. It would loiter. Then you would launch the crew. Once the crew is successfully launched, the robotic asset would then land in the Schrodinger Basin. And I should say I have a really nice video of this. I'm not going to show it to you today, but it is available for download with the Orion vehicle in cislunar space from the LPI website. Crew, once they're launched, follow a trajectory that carries them sweeping past the moon at that 100-kilometer altitude. They then go into a halo orbit around the Earth-Moon L2 position. When that blue line turns to green, that's when they have acquired the robotic asset on the floor of the Schrodinger Basin and can teleoperate the rover and guide any of the sample acquisition issues. Once the sample's been collected, there is an ascent vehicle that carries that sample into orbit, which rendezvous with the Orion capsule and then returns both crew and sample to the Earth. This is a timeline for all of the vehicles involved. This is the robotic asset. We have the launch of the Orion vehicle. Once it's successfully launched, the robotic asset descends, lands, it then rows, and here we have the L2 orbit insertion of the crew and its capture point. The green line indicates that the crew throughout that process has communication with the robotic asset, which is operating in daylight if the launch windows are well timed. Okay. Now, that is a mission that involves a single daylight period. ICEG, in trying to fulfill the global exploration roadmap, that's what this GER is all about, has been looking at what is called the Heracles Concept. This is an opportunity that includes 3 landing sites with sample return capability. The first lander deploys a rover, which collects samples. It rendezvous with the second lander. It collects samples, return them to the first lander, which then launches that first set to orbit. In this case, to an exploration deep space habitat. The rover then continues, collects another set of sample, rendezvous with the second lander. The second lander has an ascent vehicle that takes the samples up to orbit, and so on. There in total is 100 to 300 kilometer traverse capability of the robotic asset. There are 3 sample return missions encompassed within the Heracles Concept, which will return up to 60 kilograms of sediment. Oh, and I should say that Survey interns designed 2 traverses with sampling stations, relatively short and a more modest, longer traverse. I'll just drill in on the shorter one here. We land between this pyroclastic vent with ISRU potential and the peak ring of the Schrodinger Basin. All of the red dots represent stations. There are 50 stations selected for this traverse, 18 of which are sampling stations. And this would collect, over the course of all 3 missions, I should say, 50 to 60 kilograms of sample. That would be roughly 15 kilograms of sample per ascent vehicle. Okay. Thank you very much. Let me move on. Okay, that then takes us to the next phase of the ICEG Global Exploration Roadmap, which is humans to the lunar surface. ICEG has put together this type of mission opportunity. What's critical to or different here is they've actually developed this exploration deep space habitat, which is put in orbit around the Earth-Moon L2 position. There's also a large lander that deploys a lunar electric, or a lunar, I say lunar exploration rover, but that should be lunar electric rover to the surface. This is a rover that has the capacity to support a crew of 2. In this case, 1 or 2 of these LER will be deployed to the lunar surface, a crew of 4 land for 28-day to 48-day long surface missions. They have a 100-kilometer diameter exploration zone, which is the size of a site being looked at for Mars, and so this is a Mars-forward demonstration of that capability. Once samples have been collected, the crew departs in a reusable ascent vehicle, which rendezvous with the dish, and then the LER from Earth is telerobotically driven to the next landing site for the next crew. In total, There are 5 landing sites. The first one that's been selected by the ISEC group studying this goes to Malapert, Massif. The second crew goes to the South Pole Shackleton. The third crew goes to Schrödinger Basin. The fourth crew goes to Antoniadi Crater. And the fifth crew goes to the South Pole Lake and Basin interior. Per an HEOMD request, a group of survey-funded exploration science interns are currently studying the traverses for crew at each of those stations and the Trello robotic traverse between those landing sites. Okay, so I have now my conclusion slides. Brad is giving me the thumbs up. The human-assisted robotic missions will, to conclude, revalidate our ability to land and traverse the lunar surface, our ability to ascend and rendezvous in lunar orbit, and our ability to return samples to Earth, all of which are essential capabilities to be developed for the global exploration roadmap. In addition, the installation of an orbiting facility and the assembly of robotic elements at Earth-Moon L2 will validate deep space assembly, which is a Mars-forward capability, while developing the capability for crew to teleoperate surface assets, which is a Mars-forward technology. This will also demonstrate a series of crew health performance capabilities. This is a topic we don't oftentimes discuss in this group, such as deconditioning, countermeasures, space radiation protection, and monitoring, plus habitation systems, which are needed for exploration beyond the Swiss lunar environment. So, the punchline is, it's time to put the SLS and Orion capabilities to work. Let's explore and pioneer new paths. Thank you.
I'm happy to chuck this across the room at anybody. If you're sleeping, I can do that too at your head. No questions? All right. Well, the coffee's in the back, so you can be prepared for questions for the next talk. Thank you, David.